Welcome back to our podcast, where we dive deep into the fascinating world of data storage and management. Today, we're exploring how databases work, focusing on the intricacies of data storage and retrieval, the different types of storage engines, and why it's essential for applications to evolve with changing requirements. Whether you're a seasoned developer or just curious about how data systems operate, this episode is filled with insights that will help you understand the backbone of modern applications. Let's kick things off with a high-level overview of database functionality. When you store data in a database, it's important to grasp what happens behind the scenes. Databases primarily cater to two types of workloads: online transaction processing, or OLTP, and online analytical processing, known as OLAP. OLTP systems are user-facing and deal with a high volume of requests. Typically, these systems access only a small number of records per query. For example, when you check your account balance, the application uses a key to request specific records, and the storage engine employs an index to quickly locate that data. However, the speed of data retrieval often hinges on disk seek time, which can create bottlenecks. In contrast, OLAP systems are designed for analytics and are primarily used by business analysts rather than end users. These systems handle fewer queries, but each one is much more demanding, often requiring the scanning of millions of records in a short time frame. Here, disk bandwidth becomes the limiting factor instead of seek time. To tackle this challenge, column-oriented storage has become a popular solution, enabling more efficient data retrieval during complex analytical queries. Now, let's delve into the types of storage engines available. There are two main philosophies: log-structured storage engines and update-in-place storage engines. Log-structured storage engines, like Bitcask, SSTables, and LSM trees, only allow appending to files and deleting obsolete entries. They excel at converting random access writes into sequential writes, which significantly boosts write throughput, particularly on hard drives and SSDs. On the other hand, update-in-place storage engines treat the disk as a collection of fixed-size pages that can be overwritten, with B-trees being a prime example widely used in relational databases. Understanding these architectures is crucial for developers, as it equips you with the knowledge to choose the right tool for your application and adjust database tuning parameters effectively. Shifting gears, let's discuss the concept of evolvability. Applications are not static. They evolve over time as new features are added, user needs change, and business circumstances shift. This evolution often requires changes in the data stored within the application. For instance, you might need to add a new field or modify an existing record type. Relational databases typically adhere to a single schema, which can be altered through migrations, but this can be limiting. In contrast, schema-on-read databases, often referred to as schemaless, allow for a mix of data formats, accommodating both older and newer data simultaneously. This flexibility is vital for maintaining compatibility as applications evolve. As applications change, it's essential to ensure that new code can read data written by older code and vice versa. This compatibility is crucial for smooth operations, particularly during transitions. For example, when rolling out updates to server-side applications, developers may opt for a staged rollout approach. This means deploying new versions gradually, monitoring performance, and ensuring stability before a full rollout. However, client-side applications depend on users to install updates, which can introduce delays. To navigate these complexities, developers often use encoding formats like XML, protocol buffers, Thrift, and Avro. These formats assist in managing schema changes and facilitate communication between systems with varying data structures. When it comes to data representation, it's important to recognize that data exists in two primary forms. The first is in-memory representation, which includes objects, lists, arrays, and other structures optimized for fast access and manipulation by the CPU. The second is byte sequence representation, which comes into play when data is saved to a file or transmitted over a network. This process, known as encoding or serialization, differs significantly from in-memory representations. The translation between these two forms is critical. Encoding allows data to be stored and transmitted effectively, while decoding retrieves it back into a usable format. However, relying on built-in encoding methods from programming languages can lead to issues, including compatibility problems and security vulnerabilities. To mitigate these challenges, many developers turn to standardized encoding formats like JSON and XML. These formats are widely supported and promote interoperability across different programming languages. JSON, in particular, has gained popularity due to its simplicity and built-in support in web browsers. However, both formats have their downsides. For instance, XML can be verbose, and both JSON and CSV can be ambiguous in number representation. JSON, for example, doesn't differentiate between integers and floating point numbers, which can lead to inaccuracies when dealing with large values, like tweet IDs on platforms such as Twitter. In summary, understanding how databases store and retrieve data, the distinctions between OLTP and OLAP systems, and the importance of evolvability in application development is crucial for anyone working in the tech space. By grasping these concepts, you can make informed decisions about the tools and techniques you use, ensuring your applications can adapt to the ever-changing landscape of user needs and business requirements. Thanks for tuning in. We hope you found this episode enlightening. If you have any questions or topics you'd like us to cover in future episodes, feel free to reach out. Until next time, keep exploring the world of data.